Last summer, I built a lot of Pulsejet engines. The one that worked the best was probably this one. It took a few versions, but I reached this design. I 3D printed it, tested it, and it's by far one of the easiest to run alcohol Pulsejets on YouTube. I included a link if you guys want to check it out. This made me realize that I could have some interesting research material if I actually got it to run longer. The only issue with this Pulsejet is that it's a pretty large 3D print, at least by my standards, and that it runs on alcohol. Now, don't get me wrong, alcohol burns well, but there is something I have access to that works even better: nitromethane RC fuel. Now, some viewers might mention in the comments that I could always use propane or gasoline, but I do value my house and I don't want to test my insurance coverage. So this is that U-shaped version, and as you can tell, it is a really large 3D print. It's going to take me 12 hours, and I realized that I would need something that could print faster and that would also be lighter, as well as would take up less filament, and overall just be a better design. To fix this, I kept working and I made a few neat versions in between of a lot of versions. So these are a year worth of designs, and some of these worked better and some worse, so they each have their own unique advantages as well as disadvantages. I posted a few of these designs and you'll find them on my website and on my YouTube channel. Although around this time, I decided to try 3D printing my first water-cooled Pulsejet, and I quickly realized why my 3D printer isn't worth $2,000. So the black pulse jet is the one that I tried to coat in Flex Seal, and no amount of Flex Seal could make the water go all the way through. As a result, I went back to the drawing board. So this is the linear design I ended up coming up with. So it has a few advantages over the U-shaped design, primarily that it is easier to 3D print and it has a simpler geometry, so water cooling it became much easier, as well as the fact that it starts more reliably. It does produce a bit less thrust, but I'll talk about what I plan to do with that later. So I wanted to dedicate a bit of time to the actual CFD simulations I did to design this pulse jet. So this is a static pressure contour, and it shows the initial conditions of this pulse jet. So that's where the fuel would be located inside of the combustion chamber prior to ignition, and it just shows the high pressure of the initial combustion. So the next contour simply shows high pressure traveling down the tailpipe of the pulse jet. Now, this becomes really interesting when you look at the actual Mach number. So the Mach number shows that the pulse jet's exhaust is reaching Mach 2, so it's going extremely fast. However, there is some flow separation at the diffuser, and I'm going to see how I can fix that in the future version. After the combustion, there is a drop in pressure inside of the pulse jet, and this is what allows pulse jets to really function, since this is when the pulse jet draws in fresh air and reignites. Now this is really clearly shown in the actual static temperature contour, since the cooler air is shown entering the actual pulse jet's combustion chamber. This cooler, fresher air enters, and once the internal temperature is above the reignition temperature, the engine combusts and the cycle starts again. Each cycle takes 4 milliseconds to fully complete, and this means that the engine has an operating frequency of 250 Hz. This allows me to later estimate the power the engine produces, and it means that the engine detonates 250 times each second. To help guide my design for the water-cooled version, I also installed a series of thermocouples across several non-cooled versions of this Pulsejet engine. Those thermocouples are shown in the positions I've shown in this video, and they were critical in obtaining important data to be able to guide my decision for where the water cooling would take place, as well as how aggressive the water cooling should be. This plot shows the temperature inside the combustion chamber as obtained from the thermocouples. The temperature is extremely high for something that is 3D printed, and the information that was obtained from the thermocouples helped guide the design for the water-cooled version. This is the design that I ended up using for this experiment. This design essentially uses a spiral system to pass ice water through the combustion chamber of the engine, which was the area to be found to be most affected. Now, the files for this can be found down below in the description, and if you're enjoying this video, please remember to like and subscribe. So this is the final version I ended up constructing, and you can build it too using the files. Now, this version is the world's first ever fully 3D printed and fully reusable pulse jet engine. Despite being hard to hear, the engine continues functioning for a bit over 20 seconds, which is as long as its fuel capacity will allow it to function. Now, in this plot near the top, you can see the internal combustion chamber's temperature, which I measured using a thermocouple, as well as the actual temperature difference between the water that was flowed into the pulse jet and the water that came out. By using these two equations, as well as by using the temperature that was obtained from the thermocouples and any data that was extrapolated from those temperatures, I was able to find that the design that is water cooled does in theory work extremely well up until 120 seconds. Now, I checked the pulse jet after functioning and I found no real visible damage inside of the pulse jet, despite having been ignited several different times. This therefore makes it the world's first fully reusable 3D printed pulse jet engine. However, despite its achievements, this engine does have some major drawbacks, primarily with regards to its thrust. Now, this plot shows what the thrust is estimated to be based off of the simulation, and for the clean pulse jet, which is the version I tested and showed in this video, the pulse jet only provides around zero point 0.8 newtons worth of thrust. However, I have presented an abstract to SciTech in Orlando in which I plan to optimize the engine as well as introduce a fixed geometry Tesla valve to increase the thrust. In the plot, I show a blue line. This line is what was estimated from some very simple simulations without any optimization to be the thrust increase. Now, by further optimizing the valve, I would be able to get above the zero point 0.8 newtons benchmark. So the initial version of the Tesla valve jet engine I simulated was able to increase the thrust to 1.2 newtons. Now keep in mind this is without any sort of actual optimization or important analysis that was done. Oh yeah, thanks for watching and hopefully I'll post the next video soon.